Assalamualaikum warahmatullahi wabarakatuh. My name is Akmal Haziq, and today I'm going to present the lab presentation for control volume. So firstly, we will go to the introduction and we'll look at the objectives and methodology, setup of the experiment, results and discussion, and then conclusion. So firstly, introduction. Moving fluid in natural or artificial systems may exert forces on objects in contact with it. To analyze fluid motion, a finite region of the fluid, which is control volume, is usually selected, and the gross effects of the flow, such as its force or torque on an object, is determined by calculating the net mass rate that flows into and out of control volume, and these forces can be determined as in solid mechanics by the use of Newton's second law or by the momentum equation. The force exerted by a jet or fluid on a flat or curved surface can be resolved by applying momentum equation. And the study of these forces is essential to the study of fluid mechanics in hydraulic machinery. In the type of water turbine referred to as Pelton Wheel, one or more water jets are directed tangentially onto vanes or buckets that are fastened to the rim of the turbine disc. It may be noted that the Pelton Wheel is best suited to conditions where the available head of water is great and the flow rate is comparatively small. For example, with a head of 100 meter and a flow rate of 1 meter cube per second, a Pelton Wheel running at some 250 revolution per minute could be used to develop about 900 kilowatt, and the same water power would be available if the head were only 10 meter and the flow rate were 10 meter cube per second, but a different type of turbine would be needed. And to predict the output of a Pelton wheel and to determine its optimum rotational speed, we need to understand how the deflection of the jet generates a force on the buckets and how the force is related to the rate of momentum flow in the jet. And in this experiment, we'll measure the force generated by a jet of water striking a flat plate or a hemispherical cup, and to compare the results with the computed momentum flow rate in the jet. The objective of this experiment is to investigate the reaction forces produced by the change in momentum of a fluid flow when a jet of water strikes a flat plate or a curved surface, and to compare the results from the experiment with the computed forces by applying the momentum of equation. Methodology and setup of the experiment. So this is the setup of the experiment. This is the spring supporting lever. This is the jockey weight, which will be used to counter the jet coming from the nozzle, which is coming from the water supply. And this is the fulcrum, and this is the tally to indicate whether it is stable or not. And then this is the vane, and this is the transparent cylinder, and water will go to the weighing scale. So methodology of the experiment. So firstly, the apparatus is first level and the lever brought to the balance position as indicated by the tally, with the jockey weight at its zero setting. Note the weight of the jockey, and then for diameter of the nozzle, height of the vane above the tip of the nozzle when the lever is balanced, and distance from the pivot of the lever to the center of the vane. And then water is admitted through the bench supply valve, and the flow rate increased to maximum. The force on the vane displaces the lever, which is then restored to its balanced position by sliding the jockey weight along the lever. The mass flow rate is established by collecting water over a time interval, and further observations are then made at a number reducing flow rates. About 8 readings should be sufficient enough. Next, place the jockey exactly at the desired position, and then to adjust the flow control valve to bring the lever to the balanced position. Run the experiment twice, one for flat plate, then for hemispherical cup. Note that the best way to set the conditions for reduced flow rate is to place the jockey weight exactly at the desired position first, and then adjust the flow control valve to bring the lever to the balanced position. And the condition of balance is thereby found without touching the lever, which is much easier than finding the point of balance by sliding the jockey weight. Moreover, the range of settings of the jockey position may be divided neatly into equal steps. Results and discussion. We can see that the diameter of the nozzle is constant because we use the same nozzle nozzle, which is 10 millimeter, and the cross-sectional area of the nozzle can be calculated by using the formula area equals to pi d square over 4, which results in 78.5 millimeter square, and the height of vane above nozzle tip S is 35 millimeter. Distance from center of vane to pivot of lever is 150 millimeter. Mass of jockey 0.6 kilogram, which results to the weight of 5.89 Newton. And when the jockey weight is moved at a distance from move a distance y from its zero position, the force F on the vane, which is required to restore the balance, can be calculated by using the formula F times 150 equals to W times Y, which result when we insert the value of W, we will get F equals to 589 Y over 150. The mass flow rate M in the jet is found by timing the collection of known mass of water. The velocity U1 of the jet as it leaves the nozzle is found from the volumetric flow rate Q and the cross-sectional area of the nozzle. And U0 equals to U1 square minus 2GS. And U0 might has lower volume from U1 because of gravitational effect, and U1 is velocity when the jet strikes the plate. And after inserting S to the equation, we can get U0 equals to U1 square minus 0.687 of 1 over 2, which is the square root of this one. And mass flow rate is the mass of water collected determined by period of time, and momentum flow in jet at impact J equals to mass flow rate M divided times U0. So results and discussion. So firstly, we will take a look at the results for a flat plate. So in order to gather 30 kilogram of water, we need 62.2 seconds, and by using this information we can get the mass flow rate, which is kilogram over second, which results in 0.482 kilogram per second here on the first information. And we can get the value of Y, which is the displacement of the weight jockey from its zero position, which is 74 millimeter, and we can use the information to calculate U1, U0, J and F. As we can see here, when the mass flow rate decrease, right, the value of J and F also decrease. Theoretically, the value of J and F should be the same because they are countering each other. But there are a few differences here because there are some errors happening in the experiment. This is the results for the hemispherical cup. We repeat the same procedure, which is gathering a certain amount of water and calculating recording the time, calculating the mass flow rate, and we gather the value of displacement of the weight jockey Y, and we calculate the value of V1, U0, J and F. And we can see here, when the mass flow rate decrease, the value of J and F also decrease. Right? Theoretically, the value of F should be doubled by J, which means the maximum possible value of F is the doubled value of J. But there are some errors in this experiment, thus the value of F is not really doubled by J. We will see at the graph in the next slide. So in this graph, we can see that for the flat plate, the slope of the graph is 0.97 as compared with the ideal value is 1. The discrepancy is possibly due to systematic experimental errors, such as small error in measured value of the nozzle diameter. And a further possibility lies in the behavior of the jet after striking the vane. It forms a radial sheet which impinges on the inner wall of the surrounding cylinder and then divides some of the water flowing down the cylinder wall and the rest flowing upwards. Although visibility is impaired by the spray which is generated, it does seem that some water falls on the top side of the vane, which would have the effect of producing small momentum force downwards in the downwards direction, so reducing the net upward force on the vane. And for the hemispherical cup, the slope of the graph is 1.92, so that F is equals to 1.92 J. though the maximum possible force is 2G, right? Like I said earlier, the value of F should be doubled by the value of J, which occurs when the jet is deflected through 180 degree without energy loss. The ratio between measured force and the theoretical maximum may be regarded as an efficiency of the vane, 0.96 in this case, and will always be less than 1 because losses will always occur in practice. So in conclusion, the objective of the experiment is achieved. The forces produced are proportional to the rate of momentum flow, and the forces produced on hemispherical cup is higher than flat plate. And that's all from me. Thank you.